Wow, what an amazing view. We're here at the Pima Point Lookout, and we came in the morning just so we could see some of the amazing colors and features of the canyon lit up in the early morning light. And so I wanted to point out some of the layers here in the canyon. Starting at the top, you have the Kaibab limestone. And that's where we were at yesterday's lesson, where we were in the fossil beds looking at the Kaibab. The Kaibab limestone formation is often called the bathtub ring of the Grand Canyon because it's the white ring that you see all around the top of the canyon. It's a very resistant cliff-forming layer and consists of gypsum, dolostone, sandstone, red beds, chert, and limestone. It contains many marine fossils. The Toroweap Formation is a darker unit of gypsum, shale, and sandstone. It is sandwiched between the Kaibab and the Coconino formations, and because of its erodibility, it tends to be slope-forming. The tan layer underneath the Toroweap Formation is the Coconino sandstone. It's made primarily of well-sorted, fine grains of quartz and some potassium feldspar. In the Grand Canyon, it's only 65 feet thick in the west, but it thickens to over 600 feet in the middle and then thins out to 57 feet in the east. And it is less erodible than the Toroweap, and so it has a more straight cliff-forming layer. In fact, lots of times it's hard to get through that layer unless there's some faulting, so that getting passed through there. Now, there is some controversy about the formation of Coconino sandstone. Though it's largely viewed that this layer was laid down by wind deposition, more and more data is suggesting that it was actually water deposited. Proponents of the water deposition theory point to the angles of lamination of the sediment deposits, which are more typical of underwater bottom ripples than a wind-blown sand dune structure. Also, fossil tracks are commonly found in this layer, and many of the tracks show evidence of being made in a watery environment. And then after that, we have another sloping formation or layer called the Hermit Shale. Again, there are marine fossils in that layer as well. The biggest geologic group in the Grand Canyon comes right after Hermit Shale. It's the Sapai group. This group is actually made up of several erosive layers and can be easily identified by its prominent red slopes, up to 1,000 feet thick in some places, which are made up of red mudstone, sandstone, and tan limestone. Now, it too is more erodible than the others in that you'll see that slope, that telltale slope of the Sapai group. Then once you get below that long slope, you'll see a big red wall. In fact, that's what it's called. It's called the Red Wall Limestone. Now, the thing is, it's not really red. It's red because it's been stained by the iron oxides in the Sapai group. The Sapai group bleeds down into it. If you were to dig into that red wall limestone, you'd actually find that it's kind of a grayish, taupish color to it, but it's dyed red. The Mauve limestone is a yellowish-gray cliff-forming layer that varies between 350 and 600 feet thick. It is a mottled, nodular, and shaly limestone. In the eastern canyon, it forms a yellowish cliff along the lower part of the layer, a covered slope in the middle, and a ledgy red-stained cliff on the top where it borders the Red Wall or the Temple Butte limestone. Then if you look down below, you'll see kind of a greenish long slope. That is the Bright Angel Shale. The Bright Angel Shale consists of a shaly green mudstone with lesser amounts of fine-grained dark sandstone. The green color comes from the mineral glauconite, which is only known from ocean sediments, an indicator that this layer was deposited in a marine environment. Most of the formation is a sediment-covered slope or platform called the Tonto Platform, broken by low sandstone ledges. Fossils including trilobites, brachiopods, and mollusks are common in this layer. Also common are trace fossils, which include fossilized animal tracks, trails, and burrows. The Tepiz sandstone is a massive cliff-forming layer of brown sandstone, and it's very significant that it contains some coarse aggregate that's pea-sized or even larger. The base of the Tepiz layer contains a conglomerate member called the Hatata conglomerate, which contains schist and granite pebbles. So a very interesting feature in this canyon occurs below the Tepiz sandstone. So the Tepiz sandstone is below the Bright Angel Shale, and then below that Tepiz sandstone is this horizontal plane. Now, below that horizontal plane are other layers known as the basement rocks, Vishnu schist, and some other sedimentary layers, but they are actually angled upwards. But that great unconformity plane just shears them off and provides a horizontal plane on which all the other sedimentary layers are laid down on. And so from an erosion theory principle, it's very interesting to see how that erosion occurred on a large scale and then how the sedimentation happened after that. And as we talked about yesterday, I believe it happened very quickly because we see very straight lines laid down in between the different layers. No real erosional features in between them where we would expect maybe some eroding of creek beds, streams, runoff, that type of thing. But we see very flat layering